Projectile motion question here. Just want to draw your attention to the fact that we're going to be taking gravity to be 10 meters per second squared rather than the normal 9.8. We are starting above the ground and then firing off at an angle, 39 meters per second at an angle of theta, and then it hits the maximum height here above the ground. That's what we're going to be finding out in part A. Comes back down, hits the ground at C. Given conditions for the angle, of course, we could work out the angle, but actually just knowing the components is going to be absolutely fine. Let's find the maximum height. So for this is constant acceleration. I'm going to be looking, I'll call this m for the maximum height, I guess. I'm going to be looking a to m and applying suvat. I'm going to say that up is positive. And I'm going to be just working vertically, in fact. In fact, it's like sometimes you have to, well, later on you need to work horizontally as well, but let's just make it clear, vertically. Then u is going to be this component of the speed acting up. It's going to be 39 sine theta, which is 39 divided by 13, which is 3 times 5. Actually, we just get 15. A is acting down, so it's going to be minus 10. And at the maximum height, the final velocity is 0. It's not moving up or down at just that instant. That is going to be enough to work out S. I just want to highlight that actually we're not working out the one in blue at the moment. We're actually working out this. I feel like it's actually a bit confusing putting that on. So let me just say this is what we're actually working out for the moment. So I can use suvat without t in. That's going to be v squared equals u squared plus 2as. 0 is going to be 15 squared, 225, minus 20s. That gives us s is equal to 225 divided by 20, which ends up being 11.25. Therefore, max height, bearing in mind that we started 20 meters above the ground, it's going to be 20 plus 11.25, 31.25. That is kind of exact, but we're dealing with a model here, so I'm going to, for example, we've used gravity as 10, so I'm going to write it as 31.3 meters. All right, that was part A. Just going to partition it off. Okay, now we're told that the time taken for P to travel from A to C is t seconds. Determine the value of t. So you got two options here. You could work out the time taken from A to M because we've already kind of done a lot of work there, and then do the time taken to get from M to C and add them together. But we can just do it all in one go, and that's what I'm going to do. But by all means, do it the other way. You just get a similar sort of well, you get the same answer. So I'm going to be looking vertically again. I'm going to still apply up as positive. I'll talk about that a bit more in a minute. So suvat, we've still got u as 15. We've still got a as minus 10. This time we don't know what the final velocity is, but we do know the final displacement. It's gone down by 20. Because up is positive, then s is going to be minus 20. You could alternatively have chosen down to be positive, and then s would be 20, a would be 10, and it would actually be the initial velocity that was minus 15. You're just basically timesing a Suvat equation by minus 1 all throughout. So it can work, and there's just advantages sometimes into choosing a particular direction. Like if you're throwing something down, then it makes sense to make down positive. Because something's going up here, I tend to make the initial motion the positive direction. So we're now trying to work out t. I can use s equals ut plus half at squared, which means that minus 20 is going to equal 15t minus 5t squared. This becomes 5t squared minus 15t minus 20 is equal to 0. It feels like it might factorize here, so I'm going to divide through by 5, see what happens. Normally I just stick it straight into the quadratic formula on your calculator, but arguably it's going to be quicker here because it factorizes so easily. T equals minus 1 or 4. The minus 1 is not a physical solution. It's like, it actually kind of is this part of the graph down here before it began. So T is actually 4. We can say that capital T equals 4 seconds. Okay, nicely done. That was part B. Part C says state one limitation in the model other than air resistance or the wind that could affect the answer to part B. Now you got to be careful here. It's not accepted if you start questioning the things that we're actually been told. Like we've been told that the angle is the sine theta is 5/13, so you can't say things like, well, the angle might not be that. And we're also told that it's horizontal ground. So I was tempted to say, hey, maybe the ground's not horizontal, but we've been told that it is, and so that actually doesn't count. Here's some limitations. We could say the ball will have dimensions or volume. That could potentially apply some spin. It could like curve in the air, which could affect things. I think a good one, really good one here is G. So G is we've got it as 10. I mean that's not very accurate. Um, you could even say that G isn't necessarily going to be constant, but yeah, that is okay. I'd say it's better to say that it's just not going to be 10. Other weather conditions, that is accepted. The ball is not a particle. So you don't get any marks if you do talk about air resistance or wind. If you talk about the horizontal ground, if you talk about the mass of the shape, angles not as quoted, that sort of thing. So there might be other things accepted, but these ones are the ones to focus on. Final part of this question. So we're told at the instant, actually, let me look at this version of the diagram. At the instant that P is projected, a second small ball Q is released from rest at B and moves towards C along the horizontal ground. At time t seconds, the velocity is given by this. This is going to be variable acceleration. That's how that topic is creeping into this question. Because if you differentiate, you'd get the acceleration. It's going to depend on time. Whereas otherwise, it would have to just be a function like just like 3t plus 4. Then it would you just get a constant acceleration of 3. So then given that P and Q collide at C, and we have to determine that the acceleration of Q immediately before this collision, or essentially like at the instant that it gets to C. Okay, well let's take a look at this. So I'm kind of tempted actually to write down the acceleration straight away. I know that's not quite, so it's going to be dv by dt. I'm going to need to work out k first, but it's at least a starting point. So 3k t squared plus 12t plus 3/2. Right, so how are we going to work out this value of k? Well, what we do know is that they meet at C at the same time. So we need to work out that time, in fact. And they would have traveled the same distance in that time. So what we can do is take a look back at part B actually and work out how far the first particles moved in the 4 seconds. So I'm going to be now bringing in the horizontal part. So T is now, this is kind of part C. T is going to be 4 seconds. The acceleration is actually 0, which means the final velocity is the initial velocity. You can just get rid of them. We're just going to be using speed equals distance over time, essentially, or velocity is displacement over time. So the initial u is then going to be 39 cos theta. Cos theta is 12/13. So divide by 13 again to get 3. It's going to be 36. Okay, and that means I can just use S equals UT. There's no half AT squared because A is 0. And we're going to do 36 times 4, 144. So both particles have traveled 144 meters in 4 seconds. s equals 144 when t equals 4. Well, let's then work out an expression for s. And that's actually going to be integrating the velocity. You differentiate the velocity to get the displacement, it's ds by dt, integrate to get back. So I'm going to raise the power by 1, divide by that new power. It's going to be a quarter k t to the 4. And then raise the power by 1 to 3, divide by that new power. We're going to get 2t cubed plus 3 quarters t squared. There is going to be a plus c, however. So I've now got two constants, which seems to have complicated it. But there's another piece of information I didn't really talk about, and that is that they're both starting from B at the same time. So when t equals 0, s equals 0, and that's going to mean that c is 0. Okay, that one's sorted. And then I'm going to sub in my one here. 144 is going to equal a quarter k times 4 to the 4 plus 2 times 4 to the 3 plus 3 quarters times 4 squared. This becomes 144 is 64k plus 128 plus 12. That becomes 140. So 64k is equal to 4. K is going to equal 4 over 64, or 1 over 16. So that means that A, or dv by dt, is going to equal 3 times 1 over 16, so 3 over 16 t squared plus 12t plus 3 over 2. The moment just before it hits, or the moment as it hits, is going to be when t equals 4. And this acceleration is then going to be 3 over 16 times 4 squared plus 12 times 4 plus 3 over 2, or 1.5. Actually, 4 squared is 16, so they cancel. We get 3 plus 48 plus 1.5, giving us an answer of 52.5 meters per second squared. Well done.